And next, we have our next lecturer is Quoc Le. He is currently at Google, though he is coming here to CMU to start in the fall. So we'll be very lucky to have him. Quoc has done many things in machine learning. But one of the things he was most famous for, perhaps, which got a lot of press recently, was some work that he did on deep neural networks to learn image representations. And I think the tagline the New York Times said was that people at Google, which by that they meant Quoc, and a team there, but Quoc, they trained a classifier to watch videos on YouTube, and what they discovered was images for cats. And I think that was a great, they discovered how to recognize cats from that. So that was a nice soundbite for the New York Times, certainly. But he'll talk today about one of the more fashionable, I guess, elements of machine learning right now, which is deep learning.
Yeah, thank you, Jigo. So, hi everyone. Today I'm gonna talk about deep learning. Just for an introduction, I'm currently a research scientist at the Google Brain project. Google Brain project is essentially a large-scale deep learning project. And in this set of lectures, I'm going to talk about what goes on behind the Google Brain project. Okay, so for today, I will hopefully talk about the concept of linear classifier. Then I will talk about the idea of neural networks to do nonlinear classification, and then I will talk about the backpropagation algorithm to compute the gradient of neural networks. So first, I'm going to start with a motivating example of why we need neural networks. Okay. So last Friday, after a week of thinking about deep learning, I was very tired. So I wanted to watch a movie. Okay. So I've heard a lot of good things about a recent movie called Gravity. Okay, Gravity is the name of a movie. Okay, watching a movie takes a lot of time. So I asked my friends. I have two very close friends, John and Mary, and I asked them about their ratings for this movie. Okay. I called up John and I called up Mary, and I asked them for ratings for movie. And I asked them, in the scale from 1 to 5, how would you rate this movie? So John gave, my friend John, gave a score of 3, and then Mary also gave a score of 3, from 1 to 5. So I didn't even really know, is it a stellar movie, or is it an outstanding movie, or is it a bad movie, right? But thankfully, I kept record of the previous movies for that I also get ratings from John and Mary, and it looks like this. So maybe movie name, and then Mary's rating. And then John's rating, and then whether I like the movie or not. Okay, so the first movie is Lord of the Rings. Part number 2, and Mary didn't like it, so she gave the score of 1. John liked it, and he gave a score of 5, but I didn't like it. Okay. The second movie is Star Wars, Part 1. Mary likes it, so she gave a score of 4.5. John also liked it. Okay, score of 4, and I like it. I like sci-fi movie. Okay, so the question is, with the and the bunch of other movies. And then the question is, with gravity and a rating of 3 and 3, should I like the movie or not? Okay, so that's very simple. I have the past record in a table, the ratings. And there's a new movie, 3 and 3, whether should I like the movie or not, right? That's simple. Now, looking at the table might be difficult, so I want to draw in a 2D graph where how things look like. So maybe in this axis, I'm going to draw Mary's rating. Mary's rating. Right? And then in this axis, I will draw John's rating. Right? Then maybe 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 here. So there's a bunch of movie. So Lord of the Ring is get a rating of 5 from John, right? 1 from Mary. Okay, so that's a movie. Star Wars get a rating of 4 from 4 from John, and then 4.5 from Mary. So that's a movie that I like. Okay, and then there's another bunch of movie. For example, here I also have one movie here, one movie there, and then movie there, movie there, movie there. Okay. So I draw crosses for the movies that I don't like, zeros for the movie that I like. Okay. So here's a list of movies that I have in the table. This is Star Wars. And this is Lord of the Ring. Okay? And then there's a bunch of other movies. And then here's the question. At 3.3, here, should I like the movie or not, right? So that's a simple task. Okay. So here we form the problem. We want to find a decision function to say, is this a movie that I like or not? Okay? So to make it simple, I'm going to do it in mathematics, right? So let's say x is for every. So I'm going to denote an example x to denote a vector to have Mary rating, and then John's rating. It has 2 elements in it. Okay? 2 elements. And then my decision function can be like this. It's a decision function that takes x as an input, and then it's a decision function that's going to take x as input. x1 is Mary rating. x2 is John rating. I'm going to weight the rating of John and Mary, and then, come up with a linear function to say whether I like the movie or not. So I'm going to use this to say I'm going to approximate, x with y, and y is whether I like or not, right? Right. So I'm going to have a list of examples, all these examples, and y being whether, what I like is 1 and I don't like is 0, right? So what I'm trying to do is trying to take x being the score of the two my friends and learn a linear decision function where I'm going to weight the scoring of the two of my friends to approximate the ground truth, which is whether I like the movie or not. And then perhaps after I have theta and I have b, then I'm going to multiply theta 1 with John's score, theta 2 with Mary's score, and then add b to decide whether I like the movie or not. The problem is this linear decision function right here can have arbitrary values, right? It could have 1,000, or could have 100, or could have minus 1,000. So that's problematic because my y, whether I like, only takes in two values, 1 or 0, right? So what I'm going to do is instead of having the decision function to be linear like this, I'm going to make it have bounded values. So the idea is idea number 1, bounded decision function. That is, I'm going to take x, take the decision function here and map into another leaf function called g. And the function g looks like this. That when okay, so the decision function is saying that when maybe 0.5 here. So when x is negative, the function takes 0 values, and when x is positive, the function takes 1 value, right? And in between, it could have 0 between 0 and 0, 0 and 1, you know. And this function has this following attribute that if z is this value, then g of z should look like 1 over 1 exponential of minus g. Okay? So I'm mapping my linear decision function through a nonlinear function right here so that I can obtain value of the function decision function between 0 and 1. Right? So in the future, when I compute this decision function value, then I have value between any real value between 0 and 1. And if the function value is above 0.5, then I say I like the movie. And at less than 0.5, I would say I don't like the movie. Okay? And now the problem is to learn theta 1 and theta 2 using the previous data. So here is the end, right? So using the previous value, I'm going to try to do the following. So let's say x1 is the vector value for the first movie, which is Lord of the Rings. I'm going to find b such that it approximates my y1, which is I don't like the movie, which is equal to 0 here. Okay? H x2 theta b, I'm trying to approximate y2, which is the movie that I like, which is Star Wars, right? I'm going to do that for all the movies in the record. So I have x to the n, theta b, trying to approximate y n. So this index, namely, this is the nth movie in the record. And so to do this, right, So use the past record. I want to try to approximate the decision function to the label, right? And to do so, I'm gonna do the following. I'm gonna minimize So I'm going to try to find theta and b such that the distance between my h function and the label is smallest. Right? So basically, I'm trying to minimize the sum over h of x of xi theta b minus y and where I, right? And I'm going to find I from 1 to n, maybe arc mean over theta and b, right? So my best parameters are going to be theta and b such that the decision function match up with my label. Any questions so far at this point? Okay. So to minimize this function, it turns out there's a very simple algorithm called stochastic gradient descent. Okay. The stochastic gradient descent works as follows. So it would say that to minimize the sum, you iterate every component of the sum. Right? For every iteration, you look at one part of the sum, right? One part here, and then trying to minimize the distance between the h function and the label. Now, if you do so, then the function, the overall function will fluctuate, right? So perhaps the best idea is to update slowly per example. So you could do this, right? Iterate through I, where I from 1 to n, okay? And then update for every iteration, update theta 1 minus alpha delta theta 1, theta 2, delta theta 2. And then b equal to b minus alpha delta b. Okay? With alpha is something called the learning rate. Okay? So I haven't told you how to find delta theta yet, right? What I'm trying to update here. So in the next step, I will do so. So it turns out that to find a good update for theta, delta theta 1, delta theta 2, and b are the gradient of the objective function. Right? So for example, let's say at iteration I pick example I, okay? Then you want to find delta theta I, delta 1 as the derivative of the objective function. So let's call this ji. Okay. The derivative of ji with respect to theta 1. Okay. So I call this part here I, and I say the update at iteration I is delta theta 1 is equal to the derivative of ji over d1. Okay. And that's basically the derivative of h of x I theta b minus y I squared. Okay? So you could say that's equal to 2 times derivative of I think good so far. Yes, I have a question. I will talk about it later, but let's say you can pick a small number for now. Okay? I will come back to that issue in a bit. Yeah. Yeah. Oh, okay. So right now I'm making the rule deterministic in the sense that you can pick one example at a time in order. But one way to avoid that is you shuffle the data set ahead of time so that the index of the example is basically stochastic. Okay? Okay? So now the problem is trying to take the derivative of the h function with respect to theta 1. Okay? I have a question.
The derivative of h times h minus y.
Oh, this is a minus.
No, just it's the thing inside the square. As big as it is, that's times the derivative on the outside.
2 times the derivative of this one.
But it should just be an h minus yi term, and then outside of it, all of the derivative is this term.
Okay. Yeah. So 2 times. Huh? 2 times. So this is basically ji, right? Mm-hmm. So you have 2 times the derivative of the h function. Okay. Well, so basically you get the point. Basically it's trying to, if you plug in g as a function of theta times x plus b minus y here, and then 2 times here, and take the derivative, theta 1, you get back the update, okay? The rest is just basically doing derivative on the math, right? So the idea is basically at every iteration, you find, you pick a random example, and then you compute the derivative of the objective function at that example with a particular coordinate, okay? And then make the update per iteration by using this learning rule, right? You find the derivative, and then you find the update. Okay. So I want to write down what the process of what we were doing in the following graph. So here, this is Mary's rating. This is John's rating. Okay, and then we want to find theta 1 and theta 2, and then maybe some bias, and then some nonlinear decision function, which is the g function I draw over there, and then come up with a h function, which is a function of x and theta and b. Okay? So you take in, so your decision function look at two inputs, the Mary's rating for a movie, John's rating for a movie, multiply Mary's rating with theta 1, multiply John's rating with theta 2, add some bias, map to a nonlinear function, come up with a decision function, and if the decision function is larger than 0.5, you say, I watch a movie, I should watch a movie. And if it's less than or equal to 0.5, then should not watch a movie. So turns out that I ran the simulation and it looks like this. I ran the simulation, maybe and then I ran the simulation, and then I found theta and b, and then I plot the decision function when when h is being 0.5, and it's this, right? And that means I should not watch physical gravity, by the way. That means I should not watch gravity. Okay, so I run the simulation where I iterate through all the examples several times, and then I arrive at theta and b, and I converge when theta and b don't change so much, right? And then I plot the decision function when h of x, theta b, being 0.5, and it looks like this. And because gravity line below the decision function, so it means that I should not watch the movie. Okay. So it turns out, so far I talked about the linear decision function. What you just saw so far is the fact that the decision function you just saw is linear, right? Can I put this? I only have two. So it turns out that I have another friend called Susan, and her data look like this. So there are certain movies that both John and Mary like, and she also like, but there are also movies that both of them dislike, but she likes, right? This is Susan data. So the problem is you can't come up with one linear decision function to classify these examples. Because if you draw something like that, you misclassify these examples. If you draw something like that, you misclassify these examples. Okay? So how do you come up with a decision function that can actually solve this problem? So it turns out the way to do it is, here's one simple way to classify those examples, is to take this data set and then divide it into two problems. So problem number one is classified that way, and then problem number two So I take the above problem, and then I split it into two problems. Problem number one is I have these examples, but I don't have this example over here. And then I can train the above method that I showed you earlier to have a classifier like that way. And then the second problem is I remove this example. I only keep the examples on the left here, and I train another classifier to classify example and look like that. Okay? So let's say this decision function is h1, okay? And this decision function is h2. Then what you could do to come up with a final decision function, what you could do is the following. For every movie, you map to the first decision function and the second decision function. Okay? So this is movie. This is Lord of the Ring. This is Star Wars. Okay? And then you say output value by h1, and then output value by h2, and then I like or not. Okay? So this would be h of x1. So I take the decision function that I already learned before, okay, and then I map the function x. I map every pair of ratings through the decision function, okay. Instead of mapping back through, so the table over there, the columns of the tables are basically Mary's rating and John's rating. Instead of using that, I use these as experts, okay, to classify my data. And then based on those experts, what I'm going to do is I try to approximate, learn another function, right? So I'm going to use this as input to learn another function. So I can do, maybe I come back here. So what I can do is say, if I say z is a vector where h1 of x, the I is 1 of xi, h2 of xi, then I'm going to try to learn another decision function h of z TWC to approximate my Y, right? Right? And then I run the above process again to actually try to find W and C based on the fact that I already know the parameters of H1 and H2, right? So I divided the process of classifying Susan's data into 2 steps. Step number 1 is to find H1 and H2 based on some selected data. And then once I have H1 and H2, I come back and then estimate another H function, W and C, based on parameter W and C to estimate the overall data. Okay? So the process that I just drew, to draw contrast with that figure over there, so it would look like this, Mary and John, okay? Then I map it into H1, theta 1, theta 2. H2, theta 4, theta 5, and then W1, W2, this is C, right? So the decision function I'm gonna learn can be done in 2 steps. Step number 1, I try to learn H1 and H2, right? Using some selected data, okay? And then after I learn that H1 and H2, I have theta 1 and theta 2, and theta 3, theta 4, okay? And then for every example, I'm gonna map into these two functions to have H1 and H2. And then I try to learn W1 and W2 and C using the label again for all the data I have in the record. And using that 2-stage process, I can come up with a decision function that can classify all the data. If you run the simulation, you will probably achieve that too. Is there any question at this point? Yeah.
So you selected data to learn each one, but if we don't know the decision function.
Okay, so I'm gonna get to that. But let's suppose that I can select some data. Okay, let's suppose that I can decide ahead of time that I can take the data and split it into 2 parts, where each part can be classified by a linear decision function. Let's suppose that I can do that, right? Then everything is good, right? Because I can learn the first decision function, second decision function, and weight the 2 decision function. This is expert number 1, expert number 2, and then I weight the 2 experts to come up with a new decision function, right? By the way, what I just drew to you here is called a neural network. Okay? So a neural network look like this, right? You take input, right? Multiply by some matrix, and then map to something called this function here is called the activation function. Right? And this thing here is called the hidden layer. Right? The thing that inside the neural network is called the hidden layer. Okay? And each of these nodes is called a neuron. Right? The H function is called a neuron. Okay. Yes, I have a question. So the the activation function is set. The activation function is this function right here. Right? So this function here, let's say z is this function, then it's 1 plus exponential of minus z. Okay? So this is the activation function. What you're trying to learn is trying to learn the parameter theta 1, theta 2, theta 3, theta 4, b1, b2, w1, w2, and c. Right? Those are the parameters. Everything else is set. Okay? Is that clear? I should stop here and then wait for questions because there's a lot of things going on right now. So let me clean the board and you think about it. Yes, I have a question. Yeah. Okay. So one question at a time. So the first question is how I select the data. So it turns out that that's non-trivial, right? So if I'm lucky right here because the data is in 2D, right? But if data is in like very high dimensional, then I have no chance to actually separate the data, right? So I want to do it. I want to come up with a general formulation to actually come up with all these parameters at once. Because if I don't separate the data, then I don't know how many neurons to add and how I can select my data, right? So let's suppose that I have more general neural networks that look like this. Right? Right? If I have a general neural network like that, right? How would I learn the parameters, which is all the thetas and all the w's and so on at once, right? That's non-trivial, right? So it turns out that there's an algorithm called the backpropagation algorithm to actually compute the gradient of the objective function of the objective function with respect to all the parameters in the network. Right? And to appreciate the algorithm, you have to see that is so let's write down the function for h first, okay? H maybe function of x, theta, and then w, some b, some w, some c, okay? So it's a function look like this, g, which is this function right here, right, of w1 times h times g of theta 1 x1 plus theta 2 x2 plus b plus w2 times g of theta 3 x1 plus theta 4 x2 theta 2 and then plus c. Okay, so it's a equation with a lot of parameters in here, right? So how I would go about computing the derivative of one dimension of my parameters, right? That's non-trivial. So it turns out that in mathematics, if you don't know how to so So the first observation is that h is a function of functions, right? It's a function of a lot of functions, right? So in mathematics, if you don't know how to compute the gradient of a complicated function, then you can use something called the chain rule to compute the derivative, okay? And we have an algorithm to actually implement the chain rule specifically for neural networks. It's called the backpropagation algorithm, okay? I'm going to write it down in a little bit, right? And the power of the backpropagation algorithm is that you're going to compute the derivative of every of the objective function with respect to all the parameters in the network. And the network can be any size, any you can have many layers, you can have many neurons in every layer, and it can do it. Okay, I'm gonna write the backpropagation algorithm in a little bit. Yeah. Theta? The value of theta? Yeah, that's true. Okay. That's a very complicated question. Let's see. It's true that theta, the main purpose of theta is basically trying to have a nonlinear function in the network. The purpose of nonlinear function in here is that let's suppose that you have a linear function everywhere. Okay. Let's suppose you have a linear function everywhere. Then the final function is basically a linear function of a linear function, which basically just a linear function, right? So the power of depth is not there anymore, right? So the purpose of having nonlinear function in between is the fact that you can approximate very nonlinear functions. Okay? So it's not for the purpose of regularization, which trying to make the network about it. Now, but it turns out that later on, it can also play another role because this function has bounded values, right? So let's suppose you have function that that look different. So let's suppose that I use the activation that doesn't look like that, right? But I use a function that look like that. Okay? Then this function has a lot. The output of the function has a lot of values, right? So it makes the classifier even more powerful, right? So it has other undesirable properties. But I'm gonna get to that point in a little bit. Okay? There's a lot of good questions. I think you should ask more questions because today I have very smart audience, even correcting my formulation. So, okay. So the purpose of the backprop, right? First, we should write the purpose. Is to compute the derivative of ji, right? Ji is the objective function at example I, okay? With respect to a particular parameter in the network, let's say theta, theta k, okay, where theta k is one of the weights in the network, okay. So for that, I need some notation because if I keep using, theta and then W, C, and so on, it's not general enough. So first, so we're gonna, notation. So then, okay, so I denote notation theta L I J to mean the weight at layer L, the weight or maybe the parameter at layer L that connects input neuron I to output neuron J. Okay, so for example, this could mean theta 2 connecting, maybe this is the second neuron. Let's say this is the second neuron, this is the third neuron, so that's 3. Okay, so that's the notation. This could mean theta 1 connecting second to second. Okay. And then the layers index as L1, L, and L. And L is the number of layers. So this is the input, which is John's score and Mary's score, right? And this is the output. So with this notation, then I would have h of x is equal to h at layer L is equal to g of theta of n L minus 1. This is transpose times h of L minus 1 plus b and L minus 1. Okay? And then equal to, and then h of L minus 1 is equal to g of theta and L minus 2 transpose h of. So I have the function h of x is recursively defined as it's a h of hl g. This is a parameter for the second last layer, the last layer, multiplied by the value for the input plus b, and then h1 h of l minus 1 is theta l minus 2 transpose time the input and then plus b. Okay. So this is basically how you compute, you know. So this is basically H1, okay, and this is H of L minus. This is H of L. Okay, this is H of L minus 1. Okay, and this the parameter from here to here is basically theta and L minus 1, and also B and L minus 1. Okay? Everything clear about the notation? I don't have time, right? Okay. I have 5 minutes, so I talk about the backprop algorithm. Okay. So the backpropagation algorithm looks as follows. First, you perform a feed forward step to compute H1, H2, H of L. Okay. That's simple because you can take the input, multiply by the parameter, get the output, multiply by another set of parameter, get the output, and etc. Right? You do a feed forward to compute the values of the neural network until the end. And then the second step, you say, for the output layer, compute G is the derivative of the activation function. Right? So this is for the output. And then you say perform a backward pass for L equal to N, L minus 1, and L minus 2, for each node I in layer L. Compute delta Li equal to the sum j equal to 1 SL plus 1 So you compute the dot product between your parameter and some delta of the previous layer, right? Delta of the previous layer, and then multiply with the derivative of the activation function, right? And once you compute, you do a backward pass to compute all the values of all the deltas, then you're ready to compute the derivative. Then the partial derivative delta ij at layer L is equal to HL j times delta I plus 1 delta B I L equal to delta I L plus 1. So what you do, you perform a feed-forward pass, you compute all the H, and then you compute the output layer delta 1 of NL, right? And then you perform a backward pass where you do a bunch of dot products, right? And then once you store all of your deltas, and then you take your delta, multiply by your H, right? And to get the derivative for your theta, and then take the delta as your partial derivative for B. And once you have this, then you plug in the plug in the stochastic gradient descent where you say pick example K, right? Backprop to compute delta ij layer L for example okay, and then update. Okay. So in the next lecture, I will talk about how to select alpha, and then how to make deep learning run well in practice. Okay. So this is the end of the first lecture.